we've seen in several videos that the column space of a matrix is pretty straightforward to find. In this situation, the column space of A is just equal to all of the linear combinations of the column vectors of A. So it's equal to, another way of saying all of the linear combinations is just the span of each of these column vectors. So we call this one right here A1, this is A2, A3, A4, this is A5. Then the column space of A is just equal to the span of A1, A2, A3, A4, and A5. Fair enough. But a more interesting question is whether these guys form a basis for the column space. Or even more interesting, what is the basis for the column space of A? And in this video, I'm going to show you a method for determining the basis. And along the way, we'll get an intuition for maybe why it works. And if I have time, actually I probably won't have time in this video. In the next video, I'll prove to you why it works. So what you do to figure out the basis, so we want to figure out the basis for the column space of A. Remember, the basis just means that vectors span CA. Clearly, these vectors span our column space. I mean, the span of these vectors is the column space. But in order to be a basis, the vectors also have to be linearly, let me just write, linearly independent. And we don't know whether these guys or what subset of these guys are linearly independent. So what you do, and I'm just really going to describe the process here as opposed to the proof, is you put this guy in reduced row echelon form. So let's do that. So let's see if we can do that. Let's keep our first row the same. 1, 0. Let me do it actually in the right side right here. So let's keep the first row the same. 1, 0, minus 1, 0, 4. And then let's replace our second row with the second row minus 2 times the first row. So then our second row, 2 minus 2 times 1 is 0. 1 minus 2 times 0 is 1. 0 minus 2 times negative 1. 0 minus, so that's 0 plus 2. 0 minus 2 times 0 is just 0. And then 9 minus 2 times 4 is 1. Fair enough. Now we want to zero out this guy. Well, it seems like a pretty straightforward way. It's just replace this row with this row plus the first row. So minus 1 plus 1 is 0. 2 plus 0 is 2. 5 minus 1 is 4. 1 plus 0 is 1. Minus 5 plus 4 is minus 1. And then finally, we got this guy right here. And then maybe we can just, in order to zero him out, let's replace him with him minus the first row. So 1 minus 1 is 0. Minus 1 minus 0 is minus 1. Minus 3 minus negative 1. That's minus 3 plus 1. So that's minus 2. Minus 2 minus 0 is minus 2. And then 9 minus 4 is 5. So we did one round. We got our first pivot column going. Now let's do another round of row operations. Well, we want to zero all of these guys out. Luckily, this is already 0. So we don't have to change our first row or our second row. So we get 1, 0, minus 1, 0, 4. Our second row becomes 0, 1, 2, 0, 1. And now let us see if we can eliminate this guy right here. And let's do it by replacing our blue row, our third row, with the third row minus 2 times the second row. So 0 minus 2 times 0 is 0. 2 minus 2 times 1 is 0. 4 minus 2 times 2 is 0. 1 minus 2 times 0 is 1. Minus 1 minus 2 times 1 is minus 3. All right. Now, this last guy, we want to eliminate him. And we want to turn this into a 0. Let's replace this fourth row with the fourth row plus the second row. So 0 plus 0 is 0. Minus 1 plus minus 1 is 0. Minus 2 plus minus 2 is 0. Minus 2 plus 0 is minus 2. And then 5 plus 1 is 6. 5 plus 1 is 6. We're getting close. So let's see. We have this. Let's look at our pivot entries. We have this is a pivot entry. That's a pivot entry. And this is not a pivot entry. And let's see, because it's following obviously another. This guy is a pivot entry right here, or will be. We need to zero this minus 2 out. So let's, I think we'll be done. So let me write my first row just the way it is, because everything above it is 0, so we don't have to worry about it. So my first row I can just write as 1, 0, minus 1, 0, 4. I can write my second row 0, 1, 2, 0, 1. I can write my third row as 0, 0, 0, 1, minus 3. And now let's replace my fourth row. Let's replace it with it plus 2 times the second row. So 0 plus 2 times 0, 0 plus 2 times 0, 0 plus 2 times 0. Minus 2 plus 2 times 1 is just 0. 6 plus 2 times minus 3, that's 6 minus 6, that's just 0. And there we have, we've actually put our matrix in reduced row echelon form. So let me put little brackets around it. It's not so bad if you just kind of go and just do the manipulations. And sometimes when you kind of get a headache thinking about doing something like this, but this wasn't too bad. So this is the reduced, let me just say, the reduced row echelon form of A. Let me just call that matrix R. So this is matrix R right there. Now, what do we see about matrix R? Well, it has 3 pivot entries, or 3 pivot columns. Let me square them out or circle them out. Column 1 is a pivot column. Column 2 is a pivot column. And column 3 is a pivot column. Now, and we've done this in previous videos, well, there's 2 things that you can see. These 3 columns, they're clearly linearly independent. How do we know that? Well, this guy's got a 1 where, and that's just with respect to each other. If we just took a set of, let's call this R1, R2, and this would be R3, this would be R4 right here. It's clear that the set R1, R2, and R4, it's clear that this is linearly independent. And you say, why is that? Well, look, R1's got a 1 here, while the other 2 have a 0 in that entry. Right? And this is by definition of pivot entries. Pivot entries have zeros, or pivot columns have zeros everywhere except for where they have a 1. So if for any pivot column, it will be the only pivot column that has zeros there. Or it will be the only pivot column that has a 1 there. So there's no way that you can add up combinations of these guys to get a 1. You could say 100 times 0 minus 3 times 0. You're just going to get a bunch of zeros. So no combination of these 2 guys is going to be equal to that guy. By the same reasoning, no combination of that and that is going to equal this. This is by definition of a pivot entry. When you put it in reduced row echelon form, it's very clear that any pivot column will be the only one to have 1 in that place. So it's very clear that these guys are linearly independent. Now it turns out, and I haven't proven it to you, that the corresponding columns in A, so this is R1, but at A, before we put it in reduced row echelon form, that these guys right here, so A1, A2, and A4 are also linearly independent. So A1, let me circle it, A1, A2, and A4. So if I write it like this, A1, A2, and A4, let me write it in set notation. These guys are also linearly independent, which I haven't proven, but I think you can kind of get a sense that these row operations really don't change the sense of the matrix. And I'll do a better explanation of this, but I really just want you to understand how to develop a basis for the column space. So they're linear independent, and so the next question is, do they span? Do they span our column space? And in order for them to span, obviously all of these 5 vectors, if you have all of them, that's going to span your column space by definition. But if we can show, and I'm not going to show it in this video, but it turns out that you can always represent the non-pivot columns. So you can always represent the non-pivot columns as linear combinations of the pivot columns. And we'll show, and we've kind of touched on that in previous videos where we find the solution for the null space and all of that. So these guys can definitely be represented as linear combinations of these guys. I haven't shown you that, but if you take that as kind of as on faith, then you don't need that column to span. If you did, then, or I guess a better way to think it, you don't need them to span, although they are part of the span, because if you needed this guy, you can just construct him with linear combinations of these guys. So if you wanted to figure out a basis for the column space of A, you literally just take A into reduced row echelon form. You look at the pivot entries in the reduced row echelon form of A, and that's those three. And then you look at the corresponding columns to those pivot columns in your original A. And those form the basis, because any linear combination of them, or linear combinations of them, can be used to construct the non-pivot columns, and they're linearly independent. So I haven't shown you that. But for this case, if you want to know the basis, it's just these three vectors. Sorry, it's just A1, A2, and A4. And A4 right there. And now we can answer another question. So let me say, so the basis, so A1, A2, and A4 form a basis for the column space of A, because you can construct the other two guys with linear combinations of our basis vectors, and they're also linearly independent. Now, and the next question is, what is the dimension of the basis? Or what is the dimension, not the dimension of the basis, what is the dimension of the column space of A? Well, the dimension is just the number of vectors in any basis for the column space. And all bases have the same number of vectors for any given subspace. So we have 1, 2, 3 vectors. So the dimension of our column space is equal to 3. And the dimension of a column space actually has a specific term for it, and that's called the rank. So the rank of A, which is the exact same thing as the dimension of the column space, it is equal to 3. And another way to think about it, it's the number, the rank of A is the number of linearly independent column vectors that you have that can span your entire column space, or the number of linearly independent column vectors that can be used to construct all of the other column vectors. But hopefully this didn't confuse you too much, because the idea is very simple. Take A, put it into reduced row echelon form, see what your pivot, see which row columns are pivot columns. The corresponding columns are going to be a basis for your column space. If you want to know the rank for your matrix, you can just count them. Or even if you don't want to count those, you could literally just count the number of pivot columns you have in your reduced row echelon form. So that's how you do it. In the next video, I'll explain why this worked.